Good morning. It's Friday, it's 8:30. This is the time when we're celebrating our vision research and vision research around the world. And today we have a person from another country, another continent, so from far away. But before that, I just wanted to remind you that today we're going to celebrate the 10th anniversary of Gavin Herbert Eye Institute under the leadership of our famous Barry Cooperman, Professor, Doctor, and Chief Executive.
Thank you very much.
That's only a kind of a cover, but indeed the reason why we have this celebration it is because we're going to celebrate Barry's birthday. And that's the real thing.
Thank you.
Again,
please, everyone join us tonight on the terrace at 5:30. There'll be a nice celebration.
Very well. Just remember to bring your ID. So we wanted to check because there are so many young people here. All right. With all of that, let's just go back to serious stuff, which is a vision research. And I will pass to Alex to introduce our speaker. Alexander.
Good morning, everyone. My name is Alexander Tworak. I'm a project assistant in Dr. Palczewski lab, and it's my great pleasure to introduce our today's speaker, Dr. Maciej Wojtkowski. Dr. Wojtkowski is head of the Department of Physical Chemistry of Biological Systems in the Institute of Physical Chemistry of the Polish Academy of Sciences in Warsaw, as well as the co-founder and chair of the International Center for Translational Eye Research affiliated with this institute. Dr. Wojtkowski acquired his PhD in 2003 from the Nicolaus Copernicus University in Poland, PhD in physics. And in 2014, he was awarded the professorship in physics from the head of the Polish state, so the president of the Republic of Poland. From very early stages of his scientific career, Dr. Wojtkowski's research interest focused on the optical coherence tomography, so in short, OCT, which is now considered actually an indispensable medical imaging technology in our field of the ophthalmology. He is well known for the development of and optimization of the ultra high resolution, high speed spectral domain OCT, as well as work on the novel spatio-temporal OCT, about which we will hear more during today's talk. Dr. Wojtkowski is an author of over 200 publications in such prominent journals as PNAS, Nature Medicine, or Progress in Retinal and Eye Research, and recipient of multiple awards, including European Young Investigator Award, as well as the prize of the Foundation for Polish Science, which is actually the top individual research prize, which is awarded in the Republic of Poland. Today, Dr. Wojtkowski will give us a talk entitled Spatio-temporal optical coherence tomography, a new way of structural and functional eye imaging. So without further ado, I'd like to welcome our today's speaker, Dr. Maciej Wojtkowski.
Okay, thank you, Alex, for this kind introduction. Can you hear me well?
Yes. Yes.
Okay, perfect. So, yes, because of this beautiful anniversary, I would like to congratulate Professor Cooperman of creating such a beautiful environment for top research in vision science. So I have to little bit disappointed because my core expertise is not in vision science. I'm physicist and I'm doing optics. So today I'm going to talk a little bit about optical imaging. So I will give you a little bit release from hardcore research and science and talk more about the technological developments. So as Alex mentioned, I'm chairing this new facility of International Center for Translational Eye Research. We have 5 groups there, and currently within my group, which is Physical Optics and Biophotonics group, we have 6 beautiful projects, and some of them are related to vision science, like to photon vision, but most of them is more about translational optics or fundamental optics. And today I would like to talk about one of these projects, which is the development of new imaging technology with its functional modality called spatio-temporal optical coherence tomography and optoretinography. So the main motivation for this work is actually that the limitations of the current functional imaging techniques are quite severe, and it is very hard to validate and quantify new therapies. Especially this is important in emergence of new ophthalmic therapies like gene therapies, regenerative stem cells patching, precise surgery, or pharmacological control of protein activity. And the gold standard in functional visual testing is visual acuity testing that is present in almost 100% of busy ophthalmic practice. The second one is visual field examination, but more comprehensive and objective testing like electroretinography, VIPs, or cone contrast, microperimetry are performed only in less than 1% of cases. So it's not really significant part of eye care. And
if I may interrupt you for 1 second, I think you on a wrong presentation. You should change it to yes.
Okay.
Yes, good.
Ah, beautiful. Thank you. So the gold standard in objective functional photoreceptor testing and retinal testing is electroretinography, ERG. And here we have example of a typical protocol for a full field ERG that consists of 4 tests, and 2 of them are scotopic, performing scotopic conditions. So that means that patient must stay and spend at least 40 minutes or 1 hour for this testing. So it's there is also a way of finding the geographical distribution of retinal generated potentials by multifocal ERG, but still the results are highly variable between clinics, and also this test requires a very highly qualified personnel and full cooperation of patients, and that is the main reason why this testing is not performed so often. So there is, at the other end, there is optical coherence tomography that is currently becoming a standard imaging technique in ophthalmology. And this is so OCT delivers mostly the structural information about the human retina and cornea, but because the most of the pathological phenotypes in ocular diseases are they usually take form of distinct structural changes in constructed images, it is quite easy to introduce biomarkers, reliable objective biomarkers that can track the progression of the disease and potential therapies simply by using morphometry. So analyzing the thicknesses, the volumes of a fluid, shape of vessels, or other distributions of drusen and so on. So this test currently is performed in almost 30% the cases in clinical practice, and in future maybe even present in more percent, because the instruments are getting cheaper and more accessible to technical staff. So I was asked to talk a little bit about the principles of optical coherence tomography, just to introduce. So the best way to understand optical coherence tomography is to think about ultrasound imaging. But instead of using short pulses of sound waves, in OCT, there are short pulses of light. And then we focus beam in one position on the object and reconstruct the profile of the backscattered intensity versus depth. So it is done by measuring the distance or some time of flight of this pulse that was reflected back from different parts of human cornea or retina. But it is impossible to measure it directly, like in ultrasound, because the speed of light is too high. So we need to use a trick, which is called interferometry, where we can split this short pulse into two parts, and then to look at the relative delay between the pulse that is reflected from the reference mirror and the pulse that all these pulses that come back from the object. And then by moving this mirror, we can just probe in space and retrieve this information about the amount of backscattered light versus depth. And in fact, there is no need even to use very short pulses, because in physics, there is always very fundamental relationship between the spectrum of light and the resolution of OCT technique. It means that when we have light that consists mainly of wavelengths, like sunlight, for example, it has many short pulses. So it's composed of many short pulses that are uncorrelated. So then this can be used also in this interferometric setup. So there are two ways of measuring OCT signals. So we can do that by moving this reference mirror and just registering this light intensity coming back from two arms, and then we will register such signals in time. Or we can use a spectrometer and then perform Fourier transformation to get back to the same reconstructions. And this profile is called optical A-scan. So again, the amplitude of these signals will correspond to the light backscattered from the object, and the position of these spikes are corresponding to the thickness or to the localization of the scattering centers in the object. And actually, the Fourier domain OCT, it has been demonstrated that it has advantage in the signal filtering, that enables to increase the signal-to-noise ratio of this method 100-fold. And the same, it can be implied that the measurement time for the same signal-to-noise ratio can be shortened 100 times. And when I look back in the development of OCT technology, it is amazing how rapid it was. Probably we can compare it only to the developments of smartphones. So this is the example. I did the first spectral domain or Fourier domain imaging of human eye in 2002 in Poland. Then next year I moved the system to Warsaw to use high power and short pulse lasers here. And we submitted this paper to Nature Medicine, but we failed. So it was finally published in American Journal of Ophthalmology. And then I moved for beautiful, fantastic postdoc to MIT with Jim Fujimoto and Jay Duker at New England Eye Center, where I built the first prototype clinical SDOCT system that was operational for at least 4 years, as far as I know, in the clinic. And so we can see the quality of these images, of cross-sectional images from retinal imaging, and compare it to the state-of-the-art of time domain OCT Stratus OCT3 at that time, so in 2003. So it was really extremely nice development in image quality and also in imaging speed. So this plot shows how rapid was this evolution of OCT instruments. So within first 15 years of presence of this technology, so starting from 1991 when it was introduced by Dave Huang and Jim Fujimoto, we had almost 10,000 times faster readout of OCT systems in 2006. So with that, we can now hope that these developments in OCT can also provide a new functionality that will enable us to also see the state of photoreceptors. So for that, we would need fast and convenient for the operator and patient measurement, fully objective, that will deliver unambiguous information about the photoreceptor activity, and that we could also treat these new readouts as a biomarkers, and that could be selective and specific enough for photoreceptor activity. So the idea is really to use some mechanism that can cause change of the optical properties of retinal neurons that can be also intrinsic and related to photoreceptor activity. And this is called optoretinography, so as an analog to electroretinography, or optophysiology if we just treat these methods more broadly to any neural tissue. So the story happened almost 20 years ago, and there were very nice papers by Tsunoda in Japan, who did fundus reflectometry on anesthetized rhesus monkeys, and they demonstrated the correlation between the reflectivity change of the fundus with multifocal ERG. And that was the first evidence that really these reflectivity changes of the fundus after the light stimulation are related to photoreceptor activity. And then Abramov with colleagues, they published the work on human eyes. Results were not so encouraging. It was only small change, but even with that, knowing this technology and the state of the development at that time, it is really a miracle that they could register these small changes. And then in 2006, Dida Bijeva published paper in PNAS showing again reflectivity change from OCT signals of the freshly excised retinas. And I was working at the time with Vivek Srinivasan at MIT, and we did experiments on a living rat eye, OCT imaging, and we showed that there is only one layer that is responsible, one retinal layer that is responsible for this reflectivity change observed after light stimulation. And actually this single retinal layer is ISOS junction. So it is just the interface between the discs of photoreceptors or a folded membrane of cones. So in this case, the expected measurement would look the following: that we have the cross-sectional image of the retina, and we can focus on the photoreceptor layer. And then when we stimulate the retina with light, then there's brightening of this ISOS junction. The problem is that as a biomarker, it's not really very good a good way of measuring the photoreceptor activity, because there is a large individual difference between measurements, and also there is a small and difficult the signals are small and difficult to measure. There is also lack of a good reference value. So it was a follow-up in many papers from Illinois group on animals and humans, but there are not conclusive data, and also there is no really translation of this technology to the clinical practice. So, but there is another effect which was observed a couple of years ago, that this intensity change is also related to very small sub-resolution change in optical thickness of outer photoreceptor segments. And this kind of biomarker is much more, is much stronger, because this is kind of a binary measurement, and that can be really significant in sense of analyzing the photoreceptor activity. So the idea is following: if we have a dark adapted retina, then we have a single pulse, and with this single pulse, we can look here now. there is elongation of outer segments of photoreceptors. So this elongation is really small, is only in the nanometer scale. So when we look at the distance between ISOS and outer segment tips, we would see the following effect. So there is a flash, and there is a small contraction, and then elongation of photoreceptors. So there are it's biphasal characteristics. So this fast response takes milliseconds, and slow response takes seconds. And this is the original plot from the beautiful paper of Hillman from Geron Hypman's group at PNAS, showing exactly the first evidence of this effect with these two phases, the fast and slow response of photoreceptors. And after that, it was a couple of follow-up papers. And in some of them, there is just the technology development described, so how to really use this or increase the sensitivity of this technique to measure such as small displacements. And in some, authors tried to explain this phenomenon. And there is, we can just sum up these works. So the slow response is attributed, there is a sum of two exponentially rising components, and component one is supposed to correspond to osmotic response to free phosphate generated by a regulator of G protein signaling. So catalyzed hydrolysis of guanosine 3-phosphate in the alpha subunit of G protein complex with phosphodiesterase. The second component can be explained as osmoelastic model of cytoplasmic swelling consequent to the swelling of the translocation of G protein subunits into the cytosol. And it was also demonstrated that this slow response can be treated as a specific biomarker of cone dysfunction in retinitis pigmentosa. Fast response, instead, it was not analyzed so carefully, but the conclusions are that the amplitude dependent of this fast response, the amplitude depends on the flash duration, and the time scale is consistent with photoactivation of photopigment molecules, and there is linear dependence on bleaching value with the photoactivation of, so is consistent with photoactivation also of photopigment molecules. So meaning that there is some evidence, initial evidence, that this effect can be related to cone and in this case, particularly cone activation and phototransduction. So with that, we proposed using a method that can be translated to the clinical use as a functional technique, which we called photopic flicker ORG. And here the idea is that we can illuminate the retina with flickering, so with flashes of light. And then we expect that photoreceptors will follow those flashes with the change of its thickness of outer segments. Of course, we are expecting that this thickness change or the optical path difference change will be very small in order of magnitude of single nanometers. So the requirement for the system that could measure such a small displacements is following that the volume registration must be done within single milliseconds, because it must be done faster than any motion of human eye, and with a significant field of view of at least 5 degrees without dark adaptation, so with photopic conditions, just to shorten this measurement time in the clinical conditions. And currently existing OCT devices are not capable of performing such measurements. So we have to think about a new idea about the new imaging method or some critical developments in OCT technology. So the standard OCT that is known in all commercially available OCT systems is based on a scanning OCT, which is kind of similar to scanning laser ophthalmoscopy in some sense. So it's improved scanning laser ophthalmoscopy. And in these systems, there is always a laser beam that is formed in such a way that is focused on the retina and then is scanned transversally to get cross-sectional images. And then the position of the beam is shifted, and then we have another cross-sectional image. And in such a way, we can build three-dimensional reconstructions. But there's always also another way of getting OCT information by so-called full-field OCT, which is more related to fundus imaging. In that sense that it can be treated as very fancy, very highly developed fundus camera. So such instruments are currently developed by at least 3 laboratories. So there is a full-field OCT developed by Pedro Messe in Langevin Institute and Institut de la Vision in Paris. And this is time domain system, so it's relatively slow and is combined with the standard scanning OCT system. Then is a Fourier domain full-field OCT by Dirk Hillman and Geron Hittman that was used previously to see this first optoretinographic reading. And our system, which is called Spatio-temporal optical coherence tomography. So with this full-field approach, where we, instead of scanning the laser beam in the eye, we are just illuminating the eye like in regular fundus camera, and then collecting the images of the eye fundus for different wavelengths, we can speed up the system at least 10 times comparing to the fastest possible scanning OCT instruments. But there is one drawback of this method, one fundamental limitation, that we have contribution of the scattering light, because in full-field OCT, there is no mechanism that would prevent light that is multiply scattered in all directions to hit the camera and contribute to interference. So with that, we have some kind of mist or haze covering OCT images, especially in choroid and photoreceptors. And this is the images from Hillman's paper, and that was the reconstruction, cross-sectional reconstruction of full-field system that they used. So in classic scanning OCT, this effect is not present because there is a very simple mechanism to reject this scattered light, which is simply a small aperture stop or pinhole in front of the detector. And the role of this pinhole plays the single mode fiber that is typically used in scanning OCT. But for full field OCT, we cannot really use the same mechanism because we will just limit our field of view. So there must be other way for doing this. And we were working actually on a project of imaging in the scattering media. So we had this model that that we have a highly scattering opaque screen, and the object is hidden behind this screen. So we can imagine that this is RPE layer and this is choroid behind the RPE. And then we look at the image on the camera in ideal case. So the point P1 should be represented in the camera in the same as exactly in the corresponding location. But when we have a scattering object in between, the energy will be distributed and some photons will hit other locations. And then we have this disruption of imaging. So we were working on the theory, the physical description of this process using so-called spatial coherence effect, but this can be very easily explained in the practical way how we perform the experiment. So simply we can to avoid this multiply scattered light contributing to our images, we can just illuminate objects with many spatial with many masks or patterns of light illuminating with different phases. So there is a spatial distribution of phases, and with that we can just get the random walk of the photons that are multiply scattered, and there will be no walk for the light that represents the point of interest that shouldn't be disturbed. And then by simply coherent summation of such images, we can reconstruct undisturbed image. So this is what we call optical crosstalk rejection, and such operation of using these multiple illumination patterns is equivalent to the control of partial spatial coherence. So the question is, and by using this technique, we can just reject all the interference that comes from this unwanted multiple scattering light, and just get the light that is not disturbed in the mirror reflected term. So this is how we can improve the image from the choroid. So we can reject all these noises and clean up, filter out the signal to get high contrast reconstructions. So practically how we can do that is, so we use the same platform like full field OCT. So there is a swept source. Instead of using spectrometer, we can just tune the laser wavelengths and then illuminate object, register the images on the camera, and also we have a reference mirror to get interference patterns. But for our use, we need to introduce this mechanism of illuminating object with different different phase patterns. So we tested a couple of different approaches. First, we used the spatial light modulator, which is the ideal tool for generating such patterns. But with SLM, we were too slow. So then we moved to deformable membrane. This is the membrane dedicated to laser projectors, and it can just randomly modulate the phase of light spatially within hundreds of kilohertz. And then we found out even best way, more robust way, by using very long multimode fiber. So in this case, simply when we use the multimode fiber, we are generating many different patterns, illuminating patterns, which are called electromagnetic modes. And for example, in the fiber that we use, we could generate 800 modes. And with the modal dispersion, we could get the modes leaving the fiber with the intervals longer than the coherence time of the light source. So meaning that we ended up with these assumed conditions that I was presenting here, that we have 800 different patterns illuminating our objects that are decorrelated. And so with this very simple and robust technique, we could build this setup that is literally, so what we have on our optical table is exactly represented here. So we have only a couple of lenses, very fast high-speed camera that enables us to register 60,000 frames per second. That gives equivalent of 30 megahertz OCT system. And then we have another camera just for preview mode to align patients, and this 300 or 200 long multimode fiber, which can be bought in any store with optical components. So with that, we could achieve all these required parameters. So high speed of acquisition, the full field imaging, so with the reduction of the scattering effects. And there is one more thing that is important for one more limitation of the scanning systems, that when we want to get very high transverse resolution, then we have to give up the imaging depth. So, for example, in standard OCT, scanning OCT, if we want to image the entire retina, which is around 500 microns, then we cannot get a higher transverse resolution than, let's say, 10 or 15 micrometers. If we, for example, use adaptive optics OCT, then we are limiting the imaging depth radically. So we will see only the part of the retina. And this is the reason why in most of OCT images, we cannot really see beautifully the microstructure of retinal layers. And with our full field system, we actually can somehow bypass this problem because we are targeting the full chorioretinal complex to be imaged. So it's around 800 microns. And we would like to get the transverse resolution at the level of 4 or 3 micrometers to see really details like photoreceptors, neural cells, or somas, or choriocapillaries system. So with our technique, we can actually correct the focus numerically and get high transverse resolution for the entire thickness of the retina. And this is just a movie showing how we can control the defocus numerically, and we can optimize this process by looking at some metrics. So this can be all done in post-processing. We don't need to use any hardware adaptive optics system. And we can also reduce the aberrations that are introduced by human eye, because the retinal imaging with OCT always relies on the optics, natural optics of human eye, which is not perfect. And in this case, we can also in post-processing compensate aberrations to get high quality images. So this is example how we can optimize the image of capillaries in the capillary plexus, and we can get sharp reconstructions. And with that, we started to image human retina. So the protocol, the imaging protocol was following. We had the optical resolution of 4.5 microns in all directions, with the voxel size 3.5 by 3.5 by 4.5 microns. And the acquisition time for single OCT volume, which you can see here, is around 8 milliseconds. So it's a really very, very high speed imaging. With that, we can repeat these measurements many times and average to get higher quality. And these are representative coronal sections from this volume, is spanning from inner limiting membrane to choroid. And this measurement was done in a close proximity of the optic disc, and here are representative cross-sectional images. And with that, we can look at retinal microstructure. So, for example, I think for the first time we were reporting the possibility to see ELM in a limiting membrane structure as some kind of collagen fibers that are covering the ELM in the place where the vitreous is detached. So this is my eye, this is a subclinical case. There is not epiretinal membrane growing yet. I hope it will be not. And then when we go deeper, we can see nicely recognized individual nerve fibers, which is also visible. We can see that also in cross-sectional images. And then without using even angio-OCT algorithms, we can see a capillary plexuses, superficial, intermediate, and deep capillary plexus. And because the measurement is very fast, so the information in one volume is stable. So we can perform many measurements and realign these tiles of mosaic to get a high resolution imaging. Sorry for that. I just need to. show that here. So with that, we can see now the wide field inner retina image. Again, we can see ELM and cross-sectional image with high transverse resolution for all layers. We can map OPL, ISOS junction, and also we can track the photoreceptor mosaic without using adaptive optics. And then we can also go to deeper layers, to choroidal layers. So this is the standard image of choroid made by with ICGA, and that shows only the projections of projection of all vessels, choroidal vessels, after administering the fluorescein. Or in this case, it's not fluorescein, it's ICG. And in OCT imaging, we can just get cross sections from different layers and appreciate here the complexity of vascular system in choroid. And this is again the imaging without use of angio OCT. We can improve even this contrast of vasculature by using angio OCT algorithms. So we use.
Maciej, can you change again to present? Okay.
Sorry. Okay. So we used for angio OCT, we use modified complex differential variance because it's a little bit, the mechanism is slightly different than in normal classic OCT imaging. Here the relative imaging time is much longer between volumes than between B-scans in classic OCT. So we have much stronger contribution from Doppler signals. That's why the modified complex differential variance was the optimal NGO algorithm for our use. And with that, we presented like full compatibility with the Triton NGO OCT imaging of the retinal vessels. So this is stock T and this is Triton. And we can also perform some binarization in post-processing and then perform also morphometry. So we we looked at the choriocapillaris layer, which is visible here in the cross-sectional image marked by this red arrow. So it's we can see it quite clearly. There is this layer between the RPE and the choroid. So we extracted this data and looked at 3 regions of interest, and we performed morphometry of these regions, looking at the local capillary density. So we assumed that, as it is shown in this electron microscopy image, choriocapillaris are remaining some kind of sponge system with the small closed loops that we can segment and calculate the number of these loops, the sizes of loops. And we compared these markers for choriocapillaris and subtler layers. So we see the large difference in the local capillary density versus the maximum loop size. And also we can see geographical difference between the fovea and the region closer to optic disc. So this is quite a significant difference that was for us kind of evidence that the structure observed here is real choriocapillaris. So then we also tested our system on cornea. In this case, the advantage of our setup is that we in full field OCT, we need to illuminate the cornea with collimated light. So that means that the light is focused on the retina, which can be dangerous for the retina. But in our system, we simply use this multimode fiber, and then we can extend the the beam on the retina to meet the safety requirements. And with that, we imaged a cornea. So we have the images shown here that are almost at the quality of confocal microscope imaging, but without need of contact here. So it's not non-contact way. So we can see epithelial cells, endothelial cells, posterior stroma, nerve fibers, and we also performed some comparative study with specular microscopy. So we introduced deep learning to segment out the endothelial cells and calculate all these parameters like cell density, cell size, the maximal cell area, and so on, and compared it to specular microscopy. So we got quite a good agreement between those values. And we also tested this system on patients. So here's a movie showing that the case where we invited a patient with rod cone dystrophy. So for this lady, it was the first time she took part in such experiments. And we were very happy because this was kind of feasibility studies. We wanted to test whether our device is also ready for measuring patients. And we were able to get the signals after 3 or 4 minutes of aligning the patient. And that was for me very great success, because it means that this method can be applicable to clinical practice. Our system is far from being really optimized for clinical use. So that means that it's really, for us, it was very big success. And here are cross-sectional images. So we can see the dystrophy, the photoreceptor dystrophy, typical image, OCT image. And when we look at the ISOS, we see some patches of missing photoreceptors. And we also looked to the choroid, and the choroidal structure was also not different than in normal eye. But we were not really following up this, so we need, of course, to construct new system that will be more robust and useful in the clinical environment, and then we will do the proper validational studies. And now we can move back to the ORG. So actually, with our stock T setup, we can clearly differentiate the ISOS and COST, which is the outer tips of cones layer. And with that, we can look at the phase, the change of a signal phase, OCT signal phase after the light stimulation. And we reproduced this biphasal curve that was presented earlier by other groups. We also tested this method with the illumination of letter E, so that is geographically limited, and we can overlay with the photoreceptor mosaic, and we are able to really detect these changes locally where the letter E was displayed. And then going to the flicker experiments, so we used extra path to deliver the stimulus light with the DMD, and these are the parameters of the system. We changed a little bit the protocol, so we imaged now with the single volume acquisition rate of 5 milliseconds. So the volume has 512 by 256 pixels and by 512. And then the OCT field of view is quite similar to the previous configuration. And we used the visible light stimulation channel, which is collinear to IR with white light LED. And we also calculated the photoreceptor cone bleaching %. And here are the results. So first we did experiments in scotopic conditions. And this is the trace of the stimulating light showing the stimulation. And then we have the response from photoreceptors. So we see again this slowly rising curve of photoreceptor outer segment thickness elongation, but on the top of it we can see oscillation that is related to our flicker stimulation. And in photopic conditions, we see clearly this kind of oscillation with the amplitude of 2 nanometers without this long rising curve that reaches hundreds of nanometers. So simply we can somehow by pre-stimulation we can saturate this curve and then focus only on the oscillations that are caused by our flicker illumination. And moreover, after the filtering, we compared the signal that we can get by Fourier transforming these oscillations, and we realized that for light adapted case, so for the photopic condition, we get a much better signal to noise ratio, and the improvement is 10 dB, meaning that there is some mechanism in the scotopic measurement that somehow gives more noise, adds more noise to the signal. So with that, we were convincing that our photopic approach is really beneficial for further clinical use. And then we tried also experiments with multiple different frequencies. So here is an example. We applied 15 and 18 hertz with the stripes, and then we were able to recognize these signals. I mean, the regions that were activated, photoreceptors were activated with these different frequencies. Then we also performed measurements by changing the flicker frequency, and we measured the amplitude of the signals, and this is the curve reproducing the amplitude of the photoreceptor response for different flicker frequencies. And we also introduced chirped light stimulus. So instead of using this measurement one by one, repeating it for different frequencies, we can just apply one measurement where we sweep the frequency and then look at the response of photoreceptors. And this is just a plot showing that there is a full correspondence of this protocol with the previously used protocol, where we measured separately the amplitude of the photoreceptor response for different frequencies individually. So and we also compared this measurement for 2 subjects, and this is the relationship. So it looks that there is individual variability of these signals, and also we tried it for the 2 different kind of stimulation, sinusoidal and rectangular, just to test the robustness of this technique. And then we also created new stock T system for mouse imaging, and this is very briefly with extra fundus camera, and these are results from wild type and albino mice. So we improved recently the quality we can see here the capillary system in mouse eye, and also we performed a single pulse rod mediated RG, so not count mediated, and we reproduced the data that were also published by Ravi Journal before, and Robert Zawadzki. So we can see very nicely this not biphasal here, because we don't see the fast response, but the slow response of the photoreceptor elongation. Okay, with that, I would like to summarize that our spatio-temporal optical coherence tomography somehow complements the OCT method with spatial coherence control, and there's a possibility to improve the coronal projections of OCT data we can reduce numerical aberration without hardware AO, and we can enhance the photoreceptor layers and look at the outer segment response to flicker stimulations. So we introduce light-adapted ORG that can be further translated to the clinical system. So we are hoping that this novel method will enable us early detection of retinal degenerations and monitor new therapies and give the reasonable biomarkers. So with that, I would like to thank all my colleagues from my group and also internal collaborators at ICTER, Andrea, Andrzej, Marcin, and Beto, and also our collaborators in ophthalmology and external collaborators and the sources of financing. And thank you very much for your attention.
Oh, there's a lot of promise in this new technology, the ORG. We can have a patient analyzed without kind of brain input, but objectively, that would be fantastic. Andrew, what do you have to say?
Yeah, thank you. That was just a really incredible talk. So inspiring to think about how it could be used clinically. From a technical standpoint, just out of curiosity, you discussed the multimode fiber and the multimode patterns of illumination. You can do 800 with multimode fiber. How many modes are actually needed to get the image that you need, do you think?
So more modes it's better, but there is a trade-off in the geometry of the optical system. So simply once we have the way of how the improvement scales, in this case, how we can suppress the crosstalk, depends on the square root of number of modes. So meaning that with the 1,000 or 1,000 modes, we have so 10 to 3, 10 to 4. Let's say with 10,000 modes, we would have a 100-fold improvement, and that would be great. Currently, we have I think suboptimal system. So the further engineering of the fiber system, fibers for this particular use would be really great.
Thank you. And if I could ask just one more question, as far as the system, what component do you think would be the biggest challenge to commercialization? I mean, I know you have this. I think you said 60 megahertz full field camera, which is there's not many cameras that can do that out there, and I know they cost a lot of money. So, is that the component, or do you think the other components could be a limitation?
That's true, but we are really hoping that the prices of the camera will go down, because there is currently appearing more and more companies. So these cameras are on the market already for some time, and recently there is a new product from Ametec, from US company, that the price is half of the price of original system. So that's very promising. It's currently is around $50,000. So we are hoping that after creating the market, these cameras the price can go down up to 20 or 10 kilo, and then it will be feasible for being used in the commercial systems. The other component that is really critical is the light source. So we use the Russian light source from Superlume company, and currently there is a ban for Russian products, and they cannot sell really these products. But there is what I heard recently, there is a competitive company in China and also in Ireland that they are starting the manufacturing new systems. So and the price of this laser is also around $10,000. And these are really the critical components. The rest of the system is relatively cheap, and 90% of the complexity is in the software. So the numerical analysis is critical here. But with the current speed of computers, it is possible to process the data relatively quickly.
Thank you. That's really incredible images. Thank you.
Okay, let's go to Zoom. Daniel.
Thank you. Hello, Marseille. It's a beautiful images. Thank you very much, and very interesting talk. So my question is about this flicker measurement. What does it really mean? As you briefly mentioned, we have shown that the negative fast response is related to electrostatic interactions in outer segment disks, where hyperpolarization due to conformational changes of photopigment causes an increase in surface tension. They stretch, the outer segment shrinks because the volume is conserved. And this signal is very fast, it's few milliseconds. But your flicker is, the signal at flicker frequencies of 25 Hertz already pretty much at zero, so it's 40 milliseconds. So it's unlikely to be that signal of conformational changes in photopigment. So it is probably just modulation of that slow expansion, which is osmotic influx of water into outer segment. And if so, then what is the new information do you see there compared to just expansion itself? Why modulation is interesting?
Yes, thank you for this question. So yeah, you are right that probably this is not necessarily corresponding to this fast responses. But there is also in this recent work published by Ram Sabesian and EdPew, they claim that there are these two different two different curves, right? The exponential curves that are overlapping. So maybe one of these mechanisms can be somehow, maybe we can differentiate between those two mechanisms, right? By using this flicker. So that could give some extra information. But from our perspective, really what is important is to adapt this technique to the clinical conditions. So, and the photopic operations is really critical here because with that we can perform such experiments much faster than slow response in dark adapted eyes. So that would be simply the main advantage from the perspective of using it in the clinical conditions. So I'm not sure if from the perspective of understanding better this process and the vision process, if there is any value, I cannot really tell you now. But also, there is, as in normal flicker ERG, there is also important the information about latency, right? And the response, like this time courses. So this can be also additional source of information, I believe.
Okay, but you should find some correlation between this flicker response and some clinical condition, right? To see if it is useful versus just expansion itself, which is very good SNR and easy to measure.
Right. So, but as I said, the system is not ready yet, but we are hoping that with the improvements of the system, we'll be able to measure patients and then start looking for biomarkers based on this effect.
Right.
Beautiful talk, and just coming from the industry side, just wanted to say when it is ready, we'd love to talk to you because I think this would be great for looking in early AMD patients, right, where you expect to see some early rod dysfunction. My question was more on the structural side. You showed some beautiful images of the nerve fiber layer bundles. I was curious, is this approach compatible with some of the work you see from Xiaolin Liu and Daniel Hammer at the FDA, where they're using speckle analysis to visualize RGCs?
Right. So we are now currently repeating the same protocols with our system, and we are getting very promising results. So in this, and the idea is really to introduce the mechanism that will not require such a long measurement. So we are now working on this speckle reduction mechanism that we are also showing in a couple of papers, but not in eye imaging, that we can implement here and get kind of comparable quality. So, but yes, this is the direction that we are also following.
Lovely. All right. Thank you.
A beautiful talk, Maciej, and really always inspiring. So my question will be, of course, could we possibly employ this fast camera in imaging? And what is the limitation? The power density we can achieve at the eye, or maybe sensitivity of this camera?
So say it again, because I didn't hear the question.
All right.
Yes.
So what would be will this be a possibility to apply this full field camera for the 2-photon imaging? So we don't have the scanning imaging into photon, but the full field imaging. And do you think the sensitivity of this camera is enough, or maybe there is not enough power density we could achieve at the pixels?
Right. Oh, okay. Thank you. Yeah, I think it's simply for 2-photon. It will be really not there will be no sensitivity in the system. So we need first, of course, to focus beam to get enough density, like power density on the retina to get 2-photon imaging, to get the fluorescence, right? So with that, we would need still to use the scanning system. But then the camera is also, so this is CMOS camera, and CMOS cameras are not so great in terms of sensitivity comparing to old CCD cameras. So they are very noisy. There's a lot of processing to get reasonable dynamic range of these systems and so on. So I think it's quite far from being used for fluorescence imaging. So there are much better solutions for that, but of course slower. But I think this particular camera is not the best. So if with some photon amplification in front of the camera, this could be possible. But then we are losing a speed advantage.
John.
Hello, great talk. I was just wondering about how long it would, I think you kind of touched upon this, but how long it usually takes to get a image using like traditional CT versus AO versus your stock T system, and how it compares to those other systems, and like how long it really takes to take a full like image. And I think that you addressed it with like this mosaic and that it's pretty fast, but typically how long? Yeah.
So typically the longest part of the measurement is the patient alignment. So, and it depends on how the system is robust and on the ergonomy of the instrument. And then the measurement is just the moment. So in our case, the measurement is much shorter than standard commercially available systems. So it really takes the like fraction of a second. Of course, repeating the full mosaics then take a couple of minutes, because patient should look in different positions, or we should implement some scanning mechanisms for that. But this is nothing really different than classical OCT measurement. With AO systems, so it depends on the setup again, because in laboratory setups it can be very different. But it would be, I guess, if all the engineering is done properly, it should be quite similar in all of the systems.
And is there a particular wavelength of light, or like, are you just using broad light, wavelengths of light to get this image, or is there a specific like wavelength of light that you're using?
Oh yeah, sorry, I was not mentioning this. Thank you for this question. So actually we use this tunable laser tuning from 800 nanometers to 870. And the 800 nanometers or 700 nanometers is really optimal, because there is still high quantum efficiency of the camera for these wavelengths. And so we cannot go really to longer wavelengths because of the cameras cost and also speed. And when we go to shorter wavelengths, there is other problem that for visible light OCT, there is too much absorption. So we cannot really penetrate deep to the choroid. So the optimal is still near infrared that gives a trade-off and some compromise between the transverse resolution and the imaging depth.
Hernan.
John and Dr. Brown already asked my questions.
Okay, Rafa.
Hi, Dr. Wojtkowski. My name is Rafa. I'm postdoc in Chris's lab. Beautiful talk, especially the choroid images. They were super amazing. I have a question related, I think, to Justin's question. How how is the technology applicable to monitoring of AMD? If there is any obstacle in monitoring very early stages that would allow early intervention?
Yeah, so we don't know yet. We don't know yet. So we need really to test it in the clinic and see how much more information we can gain. So from the perspective of choroidal imaging at this level of choriocapillaries and subtler layers, there's not much work done. Mostly it is in vitro, and there is still a lot of room really for clinical studies with this setup. So we are going to prepare the system that will be really ready for clinical studies, and then we can maybe tell a little bit more. But the hope is that ORG, this flicker ORG, would be useful to look at the early stages of AMD. Of course, early stages, because when the cost layer is disrupted, then it will be very hard to get any signal. So we must assume that retina is more or less intact for performing this kind of experiments. But we believe that there can be some clinical value of these measurements.
Thank you.
All right, and final question will go to Alex.
Yeah, I have a very actually simple question. So when you observe the changes in the length of the outer segments that are, invoked by the light pulses, do you see the changes actually of the RPE thickness as well? So in other words, is this pulse propagated to the RPE layer?
So yeah, we tried. Thank you for this question. We tried looking at the different layers, and as also other researchers reported, there are changes in the neural retina, so in the ganglion cells and IPL. But in the RPE, we don't see any impact of this outer segment elongation. So it's really like the RPE layer, and already the ROST layer, when we measure in humans, give a very, very low response. So that when we go to RPE and Brooks membrane, we don't see any phase change.
All right, Maciej, this was wonderful, and I will let Justin to make a final comments, and we thank you for your participation and teaching us so much today. Justin.
Thanks.
Oh, no, I was just going to +1 you on the photopic approach. We would love to measure these kind of responses, but it really is a deal breaker to have to dark adapt a patient in the clinic for 45 minutes. We're not going to do it. So anyway, please keep going. This would be great.
Okay, thank you.
Thanks.